Part 4 of Unit 4 is about Hess's law. Alright, Hess's law states that in going from a particular set of reactants to a particular set of products, the change in enthalpy is the same whether the reaction takes place in one step or a series of steps. What that means is we can use the enthalpy change for each step in a complex reaction to find the overall enthalpy change as if it had happened in one step. We're going to do this by adding individual steps together. Now, in this example, we need to find the enthalpy change for the following reaction. N2 plus 2O2 yields 2NO2. And they've given us the steps there. These are the steps this reaction takes to form this overall reaction. So what we need to do is cancel out things that are on both sides of the reaction arrow. So this is our target reaction. This is what we're trying to get to. If you see anything down here that's not in this target reaction, we need to find a way to cancel it out by having it show up on both sides of the reaction arrow. We can multiply these steps by coefficients if that's necessary. So let's say we needed to multiply this top reaction by 2. We'd multiply every coefficient by 2, and we would also multiply the delta H value by 2. We can also flip reactions. Let's say that we were trying to cancel out this NO, but they were both on the same side of the arrow. We could rewrite the reaction with the products on the left side and the reactants on the right side, but since we flipped the reaction, we would also have to flip the sign of the reaction. So if it was negative, it would become a positive. Now, we don't have to do any of that stuff in this example, but let's erase all this stuff and we'll start this one from the beginning. Okay, so we've got N2, O2, and NO2 in our target reaction. Step 1 has N2, O2, and NO. Step 2, it's got the NO, O2, and the 2NO2. So we're trying to get rid of this NO, this nitrogen monoxide, and if you look in the steps we have already, if we were to add these together, just pretend that we're adding these steps together, these nitrogen monoxides are going to cancel out because there are 2 of them on each side of the reaction arrow. They're not going to show up in our overall reaction. There's nothing else for us to cancel out, so we're just going to add the rest of these together and keep everything on the same side of the reaction arrow that it's currently on. So we add these together, we get N2. We've got 2 oxygens right here, so we'll write that as 2O2. And our product is going to be 2NO2. So by adding those 2 steps together, we were able to obtain our overall target reaction. And since we didn't have to make any changes to them, we didn't have to flip anything or multiply by coefficients, we can just add the delta H values together. I couldn't find a way to type the triangle in there, so anytime you see DH, that means delta H. So we just have to add 180 to negative 112, so our delta H for this reaction is going to be 68 kilojoules. Now, that was a very simple example. We'll look at a complicated one on the next page. In this more complicated example, we're trying to find the enthalpy change for this reaction right here. So this is our target. This is what we're trying to get to. We've got 4 separate steps that take place in this reaction. So we're trying to find the overall enthalpy change by combining these 4 steps. The most obvious thing that's in the steps that's not showing up in our overall reaction is water. We've got liquid water and water vapor showing up in the steps that we're going to have to try and cancel out. So that's going to be our number 1 goal. If you look at liquid water, we've already got liquid water on both sides of the reaction arrow, so we're going to leave those alone for right now. But you see we've got water vapor, water in the gas state, both on the product side. What we need to do is flip one of these so we can cancel out the water vapor. We're going to flip this second one, and we're going to put the products on the left side. We're going to flip this one instead of the bottom one because we like this liquid water where it is. So we're going to cross out this reaction right here, and we're just going to rewrite it backwards. So we're going to have B2O3 plus 3 water vapors. That's going to produce B2H6 plus 3 O2. And since we flipped the reaction, we have to flip the sign of our delta H value. So instead of being negative 2035, it's positive 2035. Now the next thing we need to look at is we've got 3 water vapors in this step that we just flipped. There's only 1 water vapor in this step up here. So we need to multiply this 4th step by a coefficient of 3. We're going to multiply both sides by 3, and that means we also have to multiply the delta H value by 3. Now the last thing that we need to get rid of is the O2. There's no oxygen showing up in our overall reaction, so we need to find a way to get rid of that. Well, we've got 3 O2s on the product side in this reaction down here. If we look at the reactant side, we've got 3 halves plus 1 half. That's just going to add up to 2 total. So what we need to do is multiply this by a coefficient so that we can get rid of some of the oxygen. A hint as to what coefficient we need to multiply it by: if you look at our target reaction, you see a 3 in front of H2. Well, on the reactant side, there's only 1 H2, so we're going to have to put a 3 here anyway. So let's multiply this entire thing by 3. And that means we'll multiply the delta H value by 3 as well. So let's go through and cancel out things that show up on both sides of the reaction arrow. We've got 3 liquid waters. Those are going to go away because there's 3 of them right here. We've got 3 water vapors. Those are going to go away because there's 3 of them down here. Now we need to cancel out the oxygens. There's 3 oxygens over here. If you add up 3 halves is the same thing as 1.5. 1.5 plus 1.5 is 3. So we've got the equivalent of 3 oxygens in these 2 parts right there. So that's canceled out the oxygens, and we've got one last thing to get rid of. B2O3 is a product up here, and since we flipped that second step, it became a reactant over here. Everything that's left, I forgot to mark these out, talked about it but forgot to mark them, everything that's left is showing up in our overall target reaction. So we have 2B plus 3H2 yielding B2H6. Now to calculate the delta H value, we're going to add all these up, but first we would multiply negative 286 times 3 and 44 times 3. And remember, that's just because we had to multiply those reactions by a coefficient of 3. So when you add all of those up, and remember we got rid of this value, we flipped the sign on it, you add those 4 steps up, you come up with the delta H value of 36 kilojoules. That was a very complicated example, but showed a lot of the process of how you have to manipulate the steps in Hess's law problems. Your question for this section: given the following data, calculate the enthalpy change for the following reaction. So manipulate these 2 steps any way you need to come up with this overall reaction, and type the delta H value for this overall reaction in the answer box.